This is a chapter 20 assignment. Okay, the first one, a uniform electric field of magnitude. So this is the electric field of magnitude, point in the positive x direction. Okay, so this is electric field. All right, find the change in electric potential energy of. Okay, so this is charge, Q equal to Coulomb. All right, as it moves from the orange to the point. Okay, so this basically this is electric field, right? Okay, point to that direction. Assume this is orange, and this is x-axis, 0 to 6.0. All right, so this is x and y. Okay, 0, 6.0, right? So here is 6.0. Okay, so find the change in electric potential energy. Okay, so what do we know here is electric potential energy equal to charge, change of potential, electrical potential, right? And also this equal to negative work done by electric field. Okay, so we use this change of potential equal to negative work done by electric field. So let's see from here, this is the amount of charge, you move from here to here. Okay, what is potential work done by electric field? All right, so you have a negative charge here, a positive charge here. This is your electrical force. Okay, you see positive charge in electric field. This is direction of electric force. And then you have displacement from here to here, you see. This is the displacement, right? And you can tell electrical force and the displacement always perpendicular to each other, which means work done equal to 0 because work equal to negative. This is a magnitude of electrical force, displacement, cosine theta, and the theta here is 90 degree. Cosine 90 is 0. Okay, so the first one from origin to here is 0. And the second from origin to 6.0, right? So this is, okay, it's same thing here, right? This is electric field, and this is origin, right? So from here to here. All right, so say this 6.0 meter. All right, in this case, so this is the field, this is the charge, this is electrical force, this is the displacement. You see, electric force and displacement parallel to each other. Okay, so keep going. Let's see, delta U equal to negative work done by electric force, negative. Okay, electric force is QE. Okay, displacement, so here from 0 to 6.0, displacement will be delta S, right? Actually equal to 6.0 cosine 0 because they are the same direction. Okay, so electrical force this direction, right? Displacement this direction. Okay, just plug in, right? So you have charge here, and you have this is electric field. Just plug in magnitude. This is 6. Okay, so from 0 to 6.0, displacement is 6. And then you have angle here, cosine 0 equal to 1. So this will be a, put together is a negative value. Okay. Third, from origin to here, all right, same thing here. Let me write here. Okay, so from origin, right, so this is origin, charge 2x, y. Okay, so 6 and 6, right? So from origin to here, this is your displacement, right? Okay, this is your electrical force. Okay, so potential equal to negative, okay, equal to negative Q E, okay, and then delta S. So this is a 6, this is a 6, this is a 6, right? 6, 6. Magnitude of displacement will be, you see, delta S here, delta S here, magnitude equal to 6 square plus 6 square, right? So it's a hypotenuse of a right triangle. okay? And then delta S, what's the angle? Angle, this is angle, right? So force and the displacement angle here is 45 degree. Okay, so you will get the answer. Also, you can do this way. You can move charge. So if you move from here to here, right? You can go through this displacement, or you can go from here, you can go through this displacement, you see, from here to here, and then from here to there. Okay, so from 0, 0 to 6.0, 0, then from 6.0, 0 to 6.0, 6.0. So you go through this route, okay? Let's get this pen, go through this one, and then goes this one. It will be same. Through this route and this route will be same, okay? Because electric force is a conservative force, work done by conservative force is path independent, as long as you know initial position and the final position. Okay, so the answer B and C will be same. All right. Second question. A uniform electric field of magnitude, this electric field point in the positive x direction. Okay, so this is electric field. Find the change in electric potential. Okay, looking for electric potential between the origin and the position, this, and this. Okay, well, this basically is a continuation of the previous question, right? So previous question, you calculate change of potential energy equal to negative this, right? Work done by electric field. Then potential difference equal to potential over charge. All right, potential energy over charge, so equal to negative. Okay, and well, you know, you always have this, right? So this is the equation. Okay, so negative QE delta S cosine theta divided by Q. Okay, so this equal to Q and Q cancelled, negative delta S cosine theta. Okay, so this will be the equation. So basically, whatever you get from the first question, you divide by this Q, divided by this Q, right, will be the answer. Or you can restart from the beginning. Okay, so use this equation. Okay, well, scenario, right? You see the first one, from here to here, right? So this is delta S, and this is electric field. You see, field, 90 degree. Second one, from here to here, right? So this is your delta S, and this is electric field. You see, magnitude, and cosine angle, cosine 0. Third one, same thing, here to here, right? So this is your electric field. This is displacement. Okay, you know, just the same thing. Number 3, parallel plate capacitor has plate separation by, okay, so this is a plate, right? Separation by 0.95 millimeter. Okay, so millimeter equal to -3 meter. Okay, keep that in mind. If the electric field between the plates has a magnitude, okay, so this is your electric field, E equal to 22.4 times 10 to the -5 Newton Coulomb. What is the potential difference? Okay, so here, this kind of problem, well, we already learned, right? So potential actually equal to E times the separation. Okay, we call this a separation D, right? In class, we already, well, potential, this is potential difference, delta U, right? And the potential difference for the parallel plates, we just use V to stand for potential difference. Okay, so here you get the positive value, which means potential on the positive plate is this much higher than negative plate. All right. Okay, number 4. A uniform electric field with a magnitude, okay, so this is the magnitude, point in the positive x direction. Okay, again, same thing. Find the change in electric potential energy when this charge, okay, so when this charge is moved, okay, so this is charge, right? So charge in the move this much in the positive x direction, right? So this is, you see, this is delta S. Okay, potential energy, right? Potential energy equal to, okay, equal to same thing, right? Equal to negative work done by electric field equal to, you see, if you have positive charge here, electric force, right? So this is electric force equal to QE equal to negative QE, and the displacement delta S, and you look at the angle cosine 0. Okay, so that's the first question. In the positive x, in the negative x-axis, okay, so same thing, right? You move this much, okay, so here is the charge, this is the displacement. Okay, so you use the same equation. You see, this is the force, right? So this is F force. You use the same equation, but now the angle here, angle between electric force and the displacement is not 0 anymore, is 180. Okay, so for second question, you need to put a 180 in the equation. Okay. Third one, the positive y direction. Okay, so here, same thing here, right? So you see this is electric field, and you move from here, move in positive y direction. Okay, electric force is here, displacement is here, 90 degree. Okay, so now the angle will be 90 degrees, so cosine 90 is 0. Okay, so you answer the question. Number 5, a uniform electric field with a magnitude of this in the negative, okay, just like this, right? In the negative x-axis, okay, in the figure. What is the difference in electric potential between B and A? B and A, basically from A to B, right? So electric potential equal to energy. You just move test charge, right, equal to negative work done by electric field on this test charge, right, equal to negative QE delta S, right, cosine theta, Q naught, right, Q naught cancel, equal to E delta S cosine theta. That's it. Okay. So what you do here is you see electric field in this problem is this, right? So potential change, basically you, this is BA, right, from A to B. So here is a displacement, okay, A to B. And electric field is, this is electric field. Okay, so potential difference equal to, okay, equal to negative, it's always there from the equation, right? E is whatever 1200, right? Delta S is this, right? So this is from here to here is a 3.0 centimeter. Okay. Well, times 3.0 centimeters is 3.0 times 10 to the negative 2 meter. And then cosine theta. You look at theta, right? So this is your E, go this way. This is your displacement, go this way, right? Angle here is 90, cosine 90, which is 0. Okay, so VA minus VA is 0. same potential, because potential difference is 0. What is the difference in electric potential between B and C? All right, so you have to move from C to B. C to B, right? So this is your displacement, which is magnitude-wise 4.0 centimeter, right? So this is delta S equal to 4.0 times 10 to the negative 2 meter, okay? You use the same equation, you see, delta V equal to negative E delta S cosine theta, all right? So you can see this is the displacement, right? And what's the electric field? Electric field will be pointing in this direction, right? You see electric field and displacement, well, in the same direction. 0 angle, right? So this equal to negative and 1200. This guy equal to 4.0 times 10 to the negative 2 cosine angle, right? Angle between displacement, right? From C to B, and electric field is 0, cosine 0. Okay, cosine 0 is 1. All right. Well, potential from C to B. Okay. Let me see. E is 1200. Yeah. Okay, no problem. Potential from C to B. This is E. Okay. So VB minus VC. VB minus VC. Yes, from C to B. Between point A. Let me see. Do I have something wrong? QE delta S. E negative. Cosine 0 is 1. Okay. C to B. VB minus along the electric field line. Potential decrease. Yeah, so B will be this much low potential than C. Yeah. So you see you get a negative value because along the electric field line potential decrease. So potential here on C is higher than B, so VB minus VC will be negative. Okay, perfect, everything right. What is the difference in electric potential? C and A, right? So from A to C. Okay, so you see from A to C, this is your displacement. Electric field this way. Angle here, what's angle here? Angle here will be slight complicated, right? Okay, so you see you have this triangle. You look at angle here. This is E. This is from A to C, right? So this is A, this is C, this is displacement. What is this angle here? This angle equal to 90 plus this angle. What is this angle? What is this angle? Okay, this angle is, you see you have a 3 here, you have a 3 here, you have a 4 here, right? 5 here. So cosine theta, no, cosine, we call this alpha. Cosine alpha equal to 3 over 3.0 over 5.0, right? So you can figure out what is alpha. Alpha equal to inverse cosine 3.0, 5.0. Okay, you get alpha. Then theta equal to 90 plus alpha. Okay. All right, so displacement here is 5.0, and you use the same equation. So equal to negative E. Displacement is, you see, 5.0 times 10 to the negative 2 meter. And cosine theta will be 90 plus, right? Plus alpha. Alpha is inverse tangent of 3.0, 5.0. Okay. So this angle is this angle larger than 90 smaller than 180. So cosine this term is a negative value, okay? And you have here, all right? So you see potential at C will be, so the whole thing will be positive, which means potential at C is higher than potential at B, potential at A. You can also go through another route, right? So from A to C, you can go this way. You can from A to B, B to C. You see? You can go through this route from A to B, then B to C. Or you can go from A to C directly. The work done by these two routes are same. All right? So you can use whatever you get from here. Because A to B is 0, B to C is this, right? So B and C will have same answer. All right. Number 6, a particle with mass. So this is mass of particle. 3.8 gram, 10 to the negative 3 kilogram. You have to use SI unit. And the charge Q equal to 0.045 coulomb is released from rest at point A. Okay, released from here, right? In the figure below. Find the electric field has, this is electric field. Okay. All right, so what will happen if we release a positive charge here? Positive charge will move under the driven of electric force. Okay, from here, directly move to somewhere, right? What speed will it have after moving through a distance 5.0? Okay, so from here, positive charge will only move this way. Okay, because you release from rest. Okay, so the displacement will be 5.0 times 10 to the negative 2 meter. So this displacement. Okay, so looking for the water speed, right? This kind of problem we use energy conservation, right? So energy conservation tells you change of kinetic energy plus change of potential equal to 0. Okay, and what's the change of kinetic? 1/2 mv final square minus 1/2 mv initial square, and the initial is 0, right? So this whole term is 0, and plus Q, whatever charge, delta V is 0. All right, so you have to know. So here we know mass of the charge. We know amount of charge. So this is 0, right? And we need to know delta V. Okay, so here's what happened. We know on the direction of electric field, right? Potential decrease. Okay, so from this position to that position, what is the potential difference? Potential difference actually is negative E delta S cosine theta. That's what we have before, right? But now you just like we just like know that this one along the electric field line potential decrease, right? Okay, so this equal to, so basically potential here is higher than potential here by E times the separation. Okay, so if we want to go over this route, same thing, right? So negative E, magnitude of E is 1200, right? Magnitude of displacement is, you see, this is 5.0 times 10 to the negative 2, right? And what's angle between them? Angle between them, so this is displacement. This is the electric field, right? Angle between them is cosine 0. Okay, so you get a negative value, which means potential here higher than that by this much. Okay, so based on this route, we'll figure out what's the delta V. Plug into this equation, you can figure out what is the speed. You see, the only thing unknown here is final speed. Suppose the particle continues moving for another this, right? What speed will it have after second? Oh, same thing, right? You see from here, 5, right? You move another 5.0 centimeter. You can use energy conservation. Same thing here, right? So now potential difference here is different, right? So it's a 5 squared minus initial 1/2 mvi squared. So this is 0. Okay, plus q delta v is 0, right? Ask is what speed would have after. Okay, so you can tell delta v now here is from here, right, to here. Okay, so well, delta v equal to negative. Okay, now the displacement is 10, right? It's not 5 anymore, it's 10. Okay, and then cosine 0. Okay, so this is delta v. All right. So you can figure this out. So this is 0, and you just plug everything in. You can figure out what's the final speed. All right. Number 7, a proton has an initial speed. So this is the initial speed. Okay. What potential difference is required to bring the proton to rest? All right. Energy conservation, right? So this is a change of kinetic plus change of potential is 0. Change of kinetic is final minus initial. And bring to rest, which means the final speed is 0, right? Plus q delta v is 0. Okay, so we know initial speed. Also, we know mass of the proton is 1.67 times 10 to the negative 27 kilogram. And the charge of proton is 1.6 times 10 to the negative 19 coulomb. All right, so only for potential difference here. What potential difference is required to reduce initial kinetic energy of a potential by a factor of 2? Okay, all right. Well, same thing, right? Same equation, but here is reduce the initial kinetic energy by 2. Okay, so what is your initial kinetic energy? Okay, so we still use the energy conservation. Delta Ke plus delta U equal to 0. Okay, so delta Ke is Kef minus Kei plus Q delta V is 0, right? Okay, so now kinetic energy by half, initial kinetic by half, right? So final will be half. So you reduce by half, which means you only have half, right? Okay, the final will be half. So half Kei minus Kei plus Q delta V is 0. Okay, keep going. Let me use this eraser. All right, so here, so this term, this one minus this one, we have negative half Kei plus Q delta V equal to 0. Okay, because you see half of this minus Ki is half, right? Half of the Ki. And what is half Ki? What is Ki? So Ki is half mvi squared. Okay, so plus Q delta V is 0. We know mass of a proton, charge of proton, initial speed of a proton, then we can figure out what is the potential difference. All right. Number 8. In the figure below, Q1 is 1.8 nanocoulomb, Q2 is negative 2.1 nanocoulomb, and the side length of this is 0.1 meter. What is electric potential at point A? All right. So electric potential V equal to K Q R. Remember this equation. This is a scalar equation. This is a sign-sensitive equation. All right, so you have a Q1, Q2 here. And what is electric potential at A? A here, right? So electric potential at A equal to electric potential at A due to Q1 plus due to Q2. Okay, keep going. Just the superposition, just add them together, right? And the side here is 0.1 meter, 0.1 meter. Okay, all right, so what is the V1? You see, this is equal to K, Q1, distance here is 0.1 meter. You see that? Okay, so due to Q2, right, plus K, Q2. What's distance? This is your distance. Okay, so you have a side 0.1 meter, side length, right? So what is diagonal here? So basically distance between A and Q2 is this diagonal, right? Diagonal will be square root times 0.1 meter. Okay, all right, because this is a 0.1, this is a 0.1. Okay, so diagonal will be Pythagorean. You see 0.1 square plus 0.1 square root. Okay, the answer will be 0.1 times square root 2 meter. Okay, so this is 0.1 times square root 2. And you just plug in, right? So K 8.99, Q1 1.8, NC negative 9, okay? 0.1 plus, 10 to the power of 9, plus 8.99, 10 to the power 9, okay? And then Q2 negative 2.1, negative 9, okay? And the 0.1 times 2, okay? So just plug in, all right? And what is electric potential at point B? Oh, same thing, right? So at B, V1 plus V2, right? So V1 is this is distance, right? And V2, that's a distance. Okay, so same thing. Number 9, how far in meter must the potential charge Q1 and Q2 be separated for the electric potential energy of the system be this one? All right, so we know if you have two charges, Q1, Q2, okay, and they separate by a certain distance, this system holds energy. The electric potential energy held by this system equal to K, Q1, Q2 divided by R, distance here, okay? All right, we'll just plug in everything. And you know, energy here is negative 106 joule. And K, Q1, 6.22 times 10 to the negative 6, Q2, negative 22.1 times 10 to the negative 6, right? Divided by distance R. Okay. You're looking for R, solve for R. Number 10, a charge of 4.07 coulomb is held at the origin. Okay, so here is, let's see, this is origin. This is a positive charge. A second charge of, okay, so this is a 4.07 microcoulomb. A second charge of this is released from rest at the position. Okay, 1.25. Okay, so this is 1.25 and 0.50. Okay, so from here, this location, so it's a positive charge released from here. All right, if the mass of the second charge, we know the mass of this guy is this, right? What is its speed when it's moved infinitely far from the origin? All right, so this kind of problem, we use energy conservation. We use Ke plus delta U, delta Ke equal to 0. Okay, so you know you release the charge from here, right? release means initial velocity equals 0. So 1/2 mv final square minus 1/2 mv I square. And also this is 0 because initial velocity is 0 plus q second charge delta v is 0. Okay, well, we know second charge, right? Amount of charge, which is this, right? But what's delta v? Well, we know mass, right? So keep going. 1/2 mv squared plus q. Delta v is the final potential minus initial potential. Okay, so this is a potential at infinity far minus initial potential. Initial potential at here. Okay, so this location. Potential I equal to 0. We know potential at infinity far due to this charge. The first charge is 0. And what's the potential due to 4.07 microcoulomb charge at this location? Okay, so Vi equal to K 4.07 times 10 to the negative 6 distance, right? So distance here, R, right? R equal to, you see, this is basically, it's a, you see this is right triangle, right? So this is 1.25, this is 0.57, right? Okay, so the distance here is the square root of 1.25 plus 0.570 square. Okay, that's it. 8.99 times 10 to the power of 9. Okay, there you go. So this is your Vi, this is Vf, you know amount of charge, okay, and you know mass of this charge, right? And looking for speed. All right, B, at what distance from the origin does the second charge attain half the speed it will have at infinite? All right, so you figure out the speed at infinite, right? So from the first question, so you know this speed at infinite. Now the question here is where? So this assumes speed at infinite, right? So you see, you start from here, go somewhere. Okay, and that location you have speed equal to half of the speed at infinite. This location, right? Ask you where is this location. Okay, so in this problem, we still same use the energy conservation, right? Same thing here. We use this equation. Okay, and so in this case, initial velocity is still 0, and the final, right? Final, this speed will be half of the speed you get from A. Okay, and then this is you know, and delta V here, Vf minus Vi. We know Vi, this is Vi, right? So we can, from this equation, we get a Vf. The only thing we don't know is Vf. Okay, we know Vf, right? Vf also equal to K, Q, R. You see that? So we know Q here. We know K, right? Looking for R, so we solve for R. Looking for R, we solve for R. Okay, so whatever R it is, that's a speed. Oh no, that is the, and what distance from the origin. Okay, so R, whatever here, is the distance from origin. Okay, number 11. Okay. Find the electric potential at point P in the figure below. All right, so you see you have charge, 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 right? You have 3 charges, 2 positive, 1 negative. Looking at potential here. All right, one by one. Potential at P equal to V1 plus V2 plus V3. Assume this is V1. No, this is Q1, Q2, Q3. Okay, And then you just look at the distance, right? So K, Q1, distance. This is your distance from P to this one, right? So this distance. What's this distance? Okay, so you have an equilateral triangle, right? So what is this distance? So if you look at this triangle, okay, so this is 1.25, half of that, 1.25 divided by 2 meter. And this one, this length, right? This length equal to, well, right triangle, right? 1.25 square minus 1.25 divided by 2 square. You see that? Square root of this. Okay, so that's the distance from, we call this R1. How's that, right? So plus K, Q2, R2 will be half of this size, right? 1.25 divided by 2, okay? And then plus K, Q3, R3. R3 is, you see this is P. Well, this is another same, right? So equal 1.25 divided by 2. Okay, this is R3. And remember, Q3 is negative. You need to put a negative sign here. Okay, whatever get it, it is. Okay, so that is your first question. Second, suppose the three charges shown in the figure above are held in place. Okay, a force charge with charge of this and a mass of this is released from rest at P. Okay, so you release charge here. What is the speed of the force charge when it has moved infinitely far away from the other three charges? Okay, so this problem uses energy conservation. Okay, energy conservation plus Q delta U is 0, right? So delta KE plus Q delta V is 0. Okay, so this one, half mv final square minus half mvi square, right? Plus Q. Final potential minus initial potential is 0. So potential at P, right? You read from there. Release means initial velocity is 0, so this is 0. Okay, so you know mass. Looking for this term, you know charge. Potential at infinity far is 0, and this is Vp is this Vp. Okay, so put it into this equation. Looking for Vf speed. Okay, next one. To operate a given flash lamp require a charge. This is the amount of charge you have. What capacitance is needed to store this much charge in a capacitor with a potential difference between its place of this? Okay, all right. So in this problem, we know amount of charge on a capacitor is 38 microcoulomb. Okay, looking for microfarad. Okay, so we can use just that. Okay, need to store, so we know potential difference is 9.0 volts. Okay, so for the capacitor, amount of charge on capacitor equal to CV, because we know the definition of capacitance equal to Q over V, right? Amount of charge on capacitor divided by potential difference. Okay, so just plug in this divided by that. But the answer asking for microfarad, right? So if you use 38 microcoulomb, right, divided by this, which you will get a microfarad. All right. Okay, plug into this equation. All right. Number 13. A parallel plate capacitor is constructed with a circular plate. Okay, so this is a circular plate, right? So it's a circular plate like that. Okay. All right, so two circular plates. Circular, right? And separate by 0.25 millimeter times 10 to the negative 3 meter. And radius 0.051 meter. And the space between the plates is filled with dielectric with K. Kappa actually. when the charge on the capacitor is this, right? So we know charge equal to 1.5 microcoulomb. The potential difference between the plate is this, V equal to 1150 volts. Okay, so in this case, what do we know here is capacitance equal to QV, right? And also capacitance equal to kappa epsilon naught A over D. Okay, that's by definition, but this is by definition of a capacitance, and also we know capacitance actually is a function of physical property. Depends on the structure, depends on dimension and geometry. All right, so basically C also equal to this equation. So we know A, what is A? It's a circular, right? So pi r squared. So we know this is r, radius with this, right? Radius, okay, pi r squared. And the D, separation, this is your separation. Epsilon naught, which is a constant, 8.85 times 10 to 12, negative 12. Okay, and from this equation you figure out the capacitance, and then you know A, you know D, you know epsilon naught, then you figure out dielectric constant. Number 14, an automatic external defibrillator device deliver this much energy, right? So we know energy, 135 joule at a voltage of this V equal to 725 volts. What is the capacitance of this device? All right, so we know capacitor, energy held by capacitor equal to 1/2 C V squared, also equal to 1/2 Q squared over C, also equal to 1/2 QV. Okay, so those three equations. Depends on what you have, right? So in this equation, we know what do we know here is voltage, right? So this is voltage. We know voltage. We know energy. Looking for capacitance, and also remember capacitance in microfarad. Whatever you get from this equation, right? Then you're looking for microfarad. Okay. Number 15, find the electric energy density between the plate of, so we know the capacitance equal to 225 microfarad, parallel plate, the potential difference between the plates, V equal to 345 volts, and the plate separate is this, so D equal to 0.223 millimeter, okay, 0.223 times 10 to the negative 3 meter. Okay, all right. And we know potential energy density. Energy density for capacitor is 1/2 epsilon naught E squared. Okay, so what did you write this in class? All right. So we know this one is a constant. What is E? E for a capacitor. If the capacitor with the charge V, then the electric field in between will be potential difference divided by the separation. Okay, so here is the separation. Just plug this into this equation. So equal to 1/2 epsilon naught V over D squared. Okay, well, you may ask where is the capacitance for the energy density. Energy density capacitance is, it's not, you don't use the capacitance in energy density. Energy here is 1/2 CV squared. Energy density equal to 1/2 epsilon naught E squared. Okay. All right. So that's all for this problem, for this assignment.